Hello and welcome back to chemistry practice. So today we're going to talk about colligative properties. And I've done this video about 5 times now, and each time I really wasn't happy with it. So I'm going to just focus on explaining what they are in this short video, and in the next video we're going to work through some problems. First of all, what are colligative properties? Right here we have a diagram. We see that we have some sort of solvent in a container. Here we have solvent again in a container and solvent in a container. Well, let's make things basic. What is solvent? Solvent is just a fancy way of saying whatever liquid that we're going to then dissolve something into. So in this scenario here, let's just say this is water. It's H2O, it's water. We have water in a container, container, container. Okay. In this container, as you notice, there's several little particles of water above it here. What is happening is little bits of water molecules are actually evaporating into the container above the liquid. This is called vapor pressure. You're probably wondering, wait a minute, how and why? I thought water boils at 100 degrees Celsius. How can little particles of water just instantaneously turn from liquid to gas and go through this phase change? And the answer is that not every single water molecule in this container has exactly the same amount of kinetic energy. Some water molecules have a lot more than others, so basically there's an average kinetic energy in here. But in the end, some water molecules have enough energy at the surface here to break away into a gas phase, and they float around the container exerting pressure. Now there's a lot of other factors here. So for instance, if I put water out in the middle of the desert, the heat, the temperature will be a factor about how fast the water molecules evaporate. Also, it has to deal with humidity in the air and vapor pressure of the air and elevation. So there's a lot of other factors in there. We don't really need to know that right now. Let's just focus on the idea that in a container, a liquid will have some molecules turn into gas and float above it, and that is vapor pressure. I'm going to skip the rest of this for a second and come back to it. Okay, we have water in a little container here. We all have talked about how water freezes at 0 degrees Celsius. So water is going from liquid into this solid phase. It's forming crystals in here. In here we have water that's above a burner. We're applying heat, somewhat similar to vapor pressure, but a little bit different. At a certain temperature, 100 degrees Celsius, it will start to boil, and all of this water will begin to turn into gas. So what happens? I'm going to go back to osmotic pressure separately. It's a little confusing. But what happens in this water container, this water, if I add a solute? What happens if I add some sort of solute to these containers? What will happen to the vapor pressure, the freezing point, and the boiling point? And does it matter what type of solute I'm using? What if I'm using sugar? What if I'm using salt? Shouldn't it make a difference? Well, colligative properties simply refer to when you add solute and you mix it in and have this solution, it changes these properties. It doesn't matter what the solute is. It just matters that the particles are there in the solvent. So, to make things simple, the particles are in the water. It doesn't matter what the particles are. It doesn't matter if they're salt or sugar. They're there, and they affect the vapor pressure, the freezing point, and the boiling point. But let's look at a little diagram here to go over vapor pressure lowering. So I have water, I add solute, let's just say it's salt or sugar, and it actually makes it more difficult for those water molecules, even the ones with higher kinetic energy, to turn into gas. This sort of helps us visualize what's going on. Here we have water. Here's the water molecules. Some of these water molecules have enough kinetic energy to turn into vapor. But now I've added, let's just say it's sugar or salt. So this is the solute particles. And as you can see at the surface, they're actually taking up space and sort of blocking some of the water molecules, which means fewer water molecules will be able to convert into gas, and the vapor pressure above this liquid will actually be lower. That basically is what is happening. Whew. That seemed like a lot of talking for a somewhat easy explanation. Let's go into freezing point depression. Okay, so remember, when this is getting colder, kinetic energy is lowering. Eventually, it will form a solid. It's going to form a crystal. But yet again, if I add a solute in here, it sort of blocks the crystals from being formed. It makes it more difficult for the crystals to form. Let's go ahead and look at this diagram. Here's a normal water with no solute added, and at a certain temperature, 0 degrees, it makes a nice ordered crystal lattice and it becomes ice. Over here, we've added salt. And as you can see, the salt sort of gets in the way of these crystals being formed, and now we have to make it colder. We have to depress the freezing point a little bit to get it to form a nice crystal lattice. What is a real-world application of this process here? Well, have you ever noticed that people put salt on roads before it's going to snow? They do that because when it snows, they're hoping that when that snow hits the ground and it turns into this slushy mess, that it actually will not freeze as easily. So you're trying to keep ice off the roads. Another thing that people do is they add antifreeze to their radiators in their car, which is water, when it gets cold in the wintertime, to try to make it so it doesn't freeze at a certain temperature. They want to lower that temperature to protect their car. Okay, we're making some progress. Now we have boiling point elevation. So yet again, at 100 degrees, we boil this water, and it starts to go through this phase change and turn into gas. But if I add solutes, so now we have a solution, which remember is solute and solvent mixed together, it actually, kind of like vapor pressure lowering, it actually makes it more difficult for some of these molecules to convert into gas. So I have to apply more heat, more kinetic energy here to get these molecules to convert into gas. So my boiling point might be elevated by, say, 1 degree or 1.5 degrees. Now, keep in mind, all of these colligative properties don't depend on the type of solute. Yet again, it could be sugar, it could be salt, it's just the fact that they are there. The second thing is, it does depend on how much of the solute is in here. So if I add more of the solute, the boiling point elevation will be higher. If I add more of the solute here, the freezing point depression will be lower. And if I add more of it here, the vapor pressure lowering will be lower, up to a certain point. So the amount of particles, the number of particles does make a difference. Remember, if I add 1 mole of something, I'm going to add 6.022 times 10 to the 23rd particles. Those particles are going to be floating around in there. That's what makes the difference. This is important to understand because later on we're going to talk about how ionic compounds dissociate into their respective ions, and they actually produce more particles. Okay, let's look at osmosis briefly. I'm not going to go over this heavily because we really don't do it in this level of chemistry in this class, but it's still important to kind of know. Here we have a tub full of water. Notice it's just 100% solvent. Okay, let's pretend I put a semi-permeable barrier right here. What is that? It's basically, think of it as like a filter that's really, really, really fine, so water can pass through it. But things that are bigger than water, slightly bigger particles, can't. Okay, if I add a solute to this side, say I'm adding just a solute to this side, not to this side, so this is just pure water and this is now a solution, some of the water is going to still go through this barrier to try to reach equilibrium over here, to sort of put more water on this side to make it so it's not as concentrated. And as you notice, the water, the solution on this side is now going up this little part of this container. Sort of weird, but that's what happens. Here's a better picture. Here's the membrane. Here we have water. Well, this is sugar, C6H12O6, sugar. I add sugar to this side. The water on this side wants to sort of go help the water over here dilute the amount of sugar that's over here. Now this is semi-permeable, which means the sugar can't go to this side of the container. It can only stay on this side. So the water is like, oh, we're going to go help you. We're going to send some more water molecules over here to make sure it's not as concentrated on this side. Now we notice that these are uneven. So what is osmotic pressure? It's the amount of pressure I would have to put on this side of this container to force the water back to this side through this semi-permeable barrier. I can't force the sugar through here, just the water. Now this osmotic pressure will obviously be higher if I add more sugar or whatever solute I'm adding. So that is another colligative property. Remember, what are colligative properties? They're just properties of solutions that depend on the amount of a solute that you're adding to them that then affect a property like boiling point, vapor pressure, or freezing point. Okay, last thing before this video is over. I just told you it doesn't matter what the solute is. It just matters how much of it there is. But what if we add different types of solute? Yet again, it kind of lied. People do that in chemistry all the time, don't they? They tell you one thing, then they tell you all these exceptions, then you get confused. Okay, here's the thing. It matters if it's ionic, an ionic compound, or a molecular compound that you're adding. Why? It's called Van Hoff's factor. This is going to be in the equation we're going to use eventually. So this is sugar. This is molecular. When I put sugar in water, if I put 1 mole of this in this container, it will break into 6.022 times 10 to the 23rd sugar molecules floating around in there. The intermolecular forces are broken. We have all of these little molecules floating around this container. Great. Over here I have salt. Salt is an ionic compound. Salt has sodium and chlorine. So it has 2 ions. It has a sodium ion, cation, and a chloride anion. Remember, when I put this in water, it breaks into its ions. It disassociates. So not only are all the little salt, think about it, we have NaCl. I obviously am just not drawing to scale. NaCl. We have all of these. It's actually a formula unit, but anyway, so these all break apart. Fine. Let's just pretend I have an NaCl here, NaCl, which wouldn't happen, but you're thinking, okay, fine, I have 6.022 times 10 to the 23rd salt particles floating around. But actually, these here also are pulled apart by dissociation. That's sort of weird to wrap your head around. So when you think about it, I don't have 6.022 times 10 to the 23rd particles of salt floating around. What do I have? I have 6.022 times 10 to the 23rd times 2. Because all of my particles here have now divided into 2 particles. So I have double the amount of solute, essentially. It's like saying I have a dozen donuts. All right, I have a dozen donuts. Great. I put them in. I don't want to draw a dozen donuts. I'm just going to draw 4 donuts. I have 4 donuts. Wait a minute, but what if I cut all my donuts in half? I don't have 4 donuts anymore. I now essentially have 8 donuts. I know we could debate about whether a donut actually has to be a circle or not, but the point is I have 8 donuts. Or I could divide them into 4 pieces. I now have 16 donuts. So if it's an ionic compound, the number of ions it dissociates into would be Van Hoff's number. In that case, I have to use it in my equation. Over here, I have calcium chloride. Well, this actually breaks into calcium on one side. There's only one calcium. It's going to be +2. And 2 chloride anions. We see a little 2 here. So there's 3 ions. So now instead of 6.022 times 10 to the 23rd particles floating around, I have 3 times 6.022 times 10 to the 23rd particles floating around. You're probably not really going to see a number higher than 5. If we look at all these different ionic compounds we've studied, most of them have anywhere from 2 to 5 different ions in them. They'll dissociate into your solvent, which is probably going to be water, but it could be some other liquid like alcohol. And then they will affect vapor pressure lowering, freezing point lowering, and boiling point elevation, because there's more particles now to block the processes from happening. And next time we're going to use this equation to solve some practice problems. Yet again, it seems really complicated. You're thinking, wow, what is this mess? But let's just look at this. This is the change in boiling point. Now, I could put a little f down here. So that would be a change in freezing point. The equation for boiling point elevation and freezing point lowering is exactly the same, except I'm using different letters and also different constants. And really, we're just going to do problems with freezing point and boiling point. I'm not really going to touch vapor pressure lowering or the osmotic pressure. This right here is a constant. See, it has a K, which normally is a constant in chemistry. And it's a boiling point constant. Notice it's molal. What does that mean? Well, we're going to be using molality of our solution in these problems, not molarity. Remember, molality is moles of solute over kilograms of solvent. Why are we using molality rather than molarity? Because we're concerned with how many moles of solute that we're adding to the solvent, because the number of particles affects the colligative property. So molality is a much better tool to use in this instance. So this will be the molality of the overall solution that we have. So I have some solution. I'm going to have to figure out the molality of the solution. Let's just say I have some water and I added some salt. Now I got to figure out the molality of this. So I have to figure out moles of salt, kilograms of water that were there to begin with. Get my molality. Van Hoff's factor. Well, then I would have to figure out if this is going to disassociate. Normally, for all of my problems I have right now, we're just going to have a 1. We'll add some molecular compounds. But if we're adding salt, it's going to be 2. If we're adding some other ionic compound, could be 3, could be 4. This number right here will be given to you in the problem. You're not going to be expected to memorize these. These are constants. Okay? So this will be given to you on a test or on a problem. This here is showing you the boiling point constant for water in Celsius and per molality of water. So don't worry about this right now. It's going to be given to you in the problem. And basically, when you start seeing these problems, we'll just start plugging in some numbers. But of course, it's never as easy as that, and there's going to be different permutations, and they're going to throw some curveballs at you, and we're going to work through some of those. Okay, well, I hope that helped you understand colligative properties and what we're about to do. So, in the next video, stick with me, we'll work through some of them, and you're going to be great on these. Okay, thanks.